Let me recall the definition of a continuous function for the case of a real valued function, that is function defined from R2 to R. Now function f defined from R2 to R is said to be continuous at the point AB if limit xy tends to AB, fxy is equal to fab. So a similar definition can be defined in the case of a function f bar defined from S to Rm, where S is a subset of Rn. So a function f bar defined from S to Rm is said to be continuous at C bar is called to C1, C2, Cn, the n tuple. If limit v bar tends to C bar, f of v bar is called to f bar of C bar, where v bar here is called to the n tuple v1, v2 dash dash vn. So this is the definition of a continuous function for a function f bar defined from S to Rm, where S is a subset of Rn. Now let us prove this theorem. That is, if f bar is differentiable at C bar, then f bar must be continuous at C bar. We have proof for the case of f defined from R2 to R that if a function is differentiable at a point, then it will be continuous. However, the converse is not true. So let us prove it for the case of f bar. So if f bar is differentiable at C bar, then f bar must be continuous at C bar. So we know that I've defined this definition of a differentiable function of function f bar at a point C bar. So using that definition, f bar is differentiable at C bar, then in that case there will exist a linear transformation Tc bar, where Tc bar is a linear transformation defined from Rn to Rm, such that f bar of C bar plus V bar is equal to f bar of C bar plus Tc bar of V bar plus norm of V bar into Ec bar of V bar, where this last term Ec bar of V bar will always tend to 0 as V bar tends to 0. So since f bar is differentiable at C bar, so we have this relation given by equation 1, where the last term Ec bar of V bar tends to 0 as V bar tends to 0. Now using this given condition 1, we need to prove that f bar is continuous at C bar. So let us take this one, V bar is equal to V1 V2 dash dash Vn, or V bar can be written as V1 U1 plus V2 U2 plus dash dash plus Vn Un, where U1 is equal to this one, n tuple 1 0 0 everywhere. Only in the first coordinate it will be 0. U2 will be equal to 0. Only in the second coordinate entry will be 1. Otherwise elsewhere it will be 0. And similarly Un will be equal to 0 0 dash dash. In the nth order or the nth coordinate, the entry here will be 1. Otherwise it will be 0 throughout. So let us now V bar is V1, V2, Vn. So you can express V bar as V1, because if you multiply V1 into U1, then it will be V1 0 0 0 plus V2 into 0 1 0 0, that is 0 V2 you'll get. And then if you add all this, then exactly you'll get n tuple V1, V2, Vn. Now letting V bar tends to 0 bar, then this equation 1, then equation 1 now will implies that f bar of C bar plus V bar, that is this one, this will be equal to f bar of C bar plus Tc bar of V bar plus norm of V bar into 0. Why? Because by the given condition on f bar to be differentiable at C bar, Ec bar of V bar will tend to 0 as V bar tend to 0. So it means by letting V bar tends to 0 bar, this equation 1 now reduces to f bar of C bar plus V bar is equal to f bar of C bar plus Tc bar of V bar plus norm of V bar into 0. Because this term Ec bar of V bar will tends approach 0 as V bar approaches 0. So now this equation can be will simplify to this one, f bar plus V bar is equal to f bar of C bar plus Tc bar of V bar. So we have this relation. Now letting V bar tends to 0, what we need to prove is that f bar of C bar plus V bar should be equal to f bar of C bar in order to conclude that the given function f bar is continuous at a point. But now we need to show that this also tends to 0. So now here we know that V1 V bar is equal to this one, V1 V2 dash dash Vn, which can be expressed as V1 U1 plus V2 U2 plus dash dash plus Vn un, where u1 is a unit vector, where the first coordinate is 1 and the second up to the nth coordinate will be 0. u2 is that one where the second coordinate is 1 or elsewhere it is 0. Similarly, the last one un is 0 throughout except the nth coordinate. So now here v bar can be expressed in this form. Now if you apply this one tc bar of v bar, let us apply this one, it will be tc bar of v1 v2 dash dash vn. But this can be written as tc bar of, it will be v1 u1 plus v2 u2 plus dash plus vn un. And this is equal to tc bar of v1 u1 plus tc bar of v2 u2 plus dash plus tc bar of vn un. Why this is possible? Because tc bar is a linear transformation. As it is a linear transformation, so tc bar of a plus b is same as tc bar of a plus tc bar of b. So since tc bar, okay, let me write it here, a plus b is same as tc bar of a plus tc bar of b. So since tc bar is a linear transformation, so tc bar of v1 u1 plus v2 u2 plus vn un can be written as tc bar of v1 u1 plus tc bar of v2 u2 plus dash plus tc bar of vn un. But u1 is a vector and v1 is a real number. So this you can take it outside. v1 tc bar of u1 plus, again here v2 is a real number, so v2 can be taken out, tc bar of u2 plus dash dash plus vn tc bar of un. Again, by the definition of linear transformation, t of this one lambda u is equal to lambda tu, where lambda is a real number. So again, since tc bar is a linear transformation, so therefore tc bar of lambda u will be same as lambda times of tc bar u if lambda is a real number. Since v1, v2, vn are real numbers, therefore tc bar of v1 u1 plus tc bar of u2 v2 plus tc bar of un vn un can be written as, you can take out this v1 outside, it will act as lambda. So v1 tc bar of u1 plus v2 tc bar of u2 plus dash plus vn tc bar of un. Now in the beginning I have taken letting v bar tends to 0 bar, that is v1 v2 dash dash vn tends to 0 bar, here means that 0 0 n tuple 0. So now this is possible if each vi tends to 0, that is v1 will tend to 0, v2 tends to 0, dash dash vn tends to 0. So now here you see that by letting v bar tend to 0 bar, equation 1 reduces to this one. F bar of c bar plus v bar is equal to f bar of c bar plus tc bar of v bar. Now we need to show that this also tends to 0 as v bar tends to 0. So now from here you see that by letting v bar tends to 0 bar, v1 will tend to 0, v2 will tend to 0, dash dash vn tends to 0. That means this last relation here will become 1. v1 becomes 0, so 0 into this will be 0 plus 0 into this will be 0. So this implies that tc bar of v bar also will tend to 0 as v bar tends to 0. So now this last equation, that is this one, will be reduced to that, okay, I can call this as equation 2. Now this equation 2 becomes what? Limit v bar tends to 0 bar, f bar of c bar plus v bar, this will be equal to f bar of c bar, because the linear transformation tc bar of v bar also, it tends to 0 as v bar tends to 0. So by definition of a continuous function on for a function f bar, this implies that f bar is continuous at c bar. So this means that if a function f bar is differentiable at c bar, then f bar is continuous at c bar. However, the converse is not true. That one I'll give you an example, and you can also consider the example of f defined from R2 to R also. The example that we have done in the class, you please go through it, where in that example we have shown that a given function is continuous but a function is not differentiable. So by taking n this one n to be 2 and m is equal to 1, then you can have a function f where a function is different, a function is continuous at a point but it is not differentiable at a point. But we always this result is always true if f bar is differentiable at c bar, then f bar is continuous at c bar, where the f bar is defined from R2 to R, or where the f bar is defined from S to Rm. And the converse is always false for both the cases, that is for this one also and for this also. And the example for this, you can consider the example that I have given for the case f defined from R2 to R. So you please go through again this explanation. If it is not clear, you please let me know.